So, we are going to touch upon the last topic of the probability today, which is called confidence intervals. Now, so far, what we've been doing is that we have been talking about two proportions. We've been talking about population proportion, P, and we're talking about the sample proportion, which is P hat. So this is the sample proportion. In all the topics that we've learned so far, in one way or the other, we had known this, more or less, right? Where, for example, we also said that the mean of your population proportion is equal to, so mean of your sample proportion is nothing but the value of the population proportion, right? If your n is a large quantity, if your sample size is large. But my point here is, how do you find this population proportion? The sheer reason of doing sampling is because you don't know about your population. It is difficult to know the characteristics you are trying to find out from your population. So for example, if I say, and I'll use the example of the book, if I want to use that how many school-going children are using social media actively across Australia. Do you think it's that easy to know? Very, very difficult, right? Unless you go and spend that amount of money where you can go and count and talk to each student of Australia and then come out with a population proportion that, all right, you had a chat with, let's say, 500,000 students, and out of that you found that like 400,000 were using the social media. But then this is, I won't say not possible, but then this will take a lot of time and material, right? So which actually is not that easy to spend and easy to measure. So the point is, how do we find this population proportion? So that is why we use sampling. That is why we use sampling. So we say, okay, out of 100,000, out of 500,000 students that I have across Australia, I just pick up random 20 different schools across Australia. I pick one student each, right? And let's say I found that 14 of them use social media. So then I say, roughly looking at this sample, my sample proportion is 0.7. 70% are using social media in my sample, and hence I can extrapolate that, or I can infer that, all right, since it is not easy for me, or it's not possible for me to go to 500,000 students, I picked up random 20 and I found 70% are using social media. So obviously population proportion would be somewhere very similar, 0.7. So that's one way. Now, if I just infer that straight away from just one sample, I might be wrong. Let's say I pick up another 20. And now this time I found, all right, I just found only 10. Then what happens? My population proportion becomes 50% or 0.5. Significantly different from my first sample. So when I'm just using a single sample and its population and its sample proportion to be almost equivalent to the population proportion, I call that as point estimates, point estimation. Then I just picked up handful, just once. I found some number of the characteristic I'm trying to measure, and I'm just talking about the population based on my sample results. This seems to be incorrect, not the right way, because the moment you pick up the second sample, you get another results. You pick up third sample, you get another results, so on and so forth. Now you can, what you can do is, you can increase your sample size. You can increase your sample size n. This is n, right? Yeah. And then you might get a 0.6. You increase to, you take another one, let's say 2000, you get 0.67, and so on and so forth. So what's happening here is that I now get, if I keep doing that, let's say if I keep picking a sample of 200 for, let's say, 10 times, 200 times 10 times, I will get 10 different values of my sample proportion. So what I will now get is, I will see, all right, what's my lowest? I say, okay, 0.4 is my lowest. What is my highest? Let's say in this case, somewhere you would have got a 0.8, let's say. So I say, okay, that's my lowest, my lower bound, and my upper bound is 0.8. Then, rather than just doing the point estimation, and I say, okay, I just picked up one sample and I just talked about, and I just extrapolated that to be my population proportion, I did not do point estimation. I took range of samples of the same size and found different sample proportions, and then I found the range, the min and the max. And now I say that I found not just a number, I found an interval. So what is this interval? So this interval tells me that my population of, let's say in this example, 500,000 students, there is a high possibility that the population proportion must be sitting somewhere in the middle. So now I'm defining an interval rather than a single number. Getting my point? So what is an interval? That is most important to know. And then we'll talk about the confidence. So does that make sense? The interval. So now let's say someone would have done this study and they found that it to be a 0.66, let's say. So you would have somewhere 0.66 sitting in. So your intervals, when you do multiple sampling, you find an interval. And you can confidently then say that I am confident that the population proportion for students in Australia using social media is between 0.4 to 0.8, which means from 40% to 80%, somewhere in between, the students are using social media. Getting my point? So this is nothing but the interval. Now let's talk about, any doubts here? Straightforward? Now let's talk about the word confidence here. Shall I take this off a bit more? Let's talk about confidence now. Now, when I say that, all right, my interval is between 0.4 and 0.8, you can ask me how sure you are, how confident you are that that's the range. Are you 10% confident? Are you 20% confident? Are you 90% confident? So I need to tell a percentage. I need to associate a percentage with my interval. That I am X% confident that my population proportion sits within this range. And that is called confidence interval. An interval for the population proportion that you have found using sample proportions is nothing but confidence interval. And every interval is attached with a level of confidence, a percentage of confidence. In the book, most of the time they talk about 95% confidence interval. So now the formula, and I'll jump onto the formula, I don't do a deep dive into how we arrived at that formula. So the formula for the 95% confidence interval is, so for the interval I need the lower bound and I need the upper bound. So the lower bound is P, so sample proportion minus 1.96 square root of P hat 1 minus P hat over N, comma. Now let's talk about the upper bound. Same story with a plus. P hat plus 1.96 square root of over N. So that is the 95% confidence. This formula gives me 95% confident interval. I'm 95% confident that whatever I'll compute using this, my population proportion will sit within this range. It's a 95% confidence level. Does that make sense, right? So we understood what is interval, we understood what is confidence, and then we talked about the 95% confidence. Right? Now, this word here, 1.96, is interesting. This number changes with the level of confidence that you're playing around every time. So 1.96 is for 95% confidence. Now, how do I get 1.96, right? I could have told you to just mug this up, but there is a reason behind it. I think in last session, we just touched upon it. So if you go to your inverse normal, open your CAS up, you've got your inverse normals. So in your inverse normal, let's say that's how it is. And I'm talking about the 95% confidence. So that means I'm talking about something like this, where this is the lower bound and that's the upper bound of the 95%. So that means that's the area under the graph for 95%. My population proportion will sit somewhere within. Now, if this is 95%, how much is this? 2.5% across? Yes? In decimals, how much would that be? 0.0025. Correct?
I think 1 0 less.
0.25 is 25%. 0.025 is what you're saying, is it? Yeah, okay. Now, go to your inverse normals. Put your area as 0.025. Put your mu equals to 0, the standard normal. And your sigma equals to 1. See, what do you get? What do you get, Chris?
Negative 1.96.
That's precisely what this is. Right? And from symmetry, this will be a positive 1.96. Right? Got it? Alright, yes? Kisha, any questions? All good? Now, there's no need to mug this up then, right? So, but then 95 you should know generally. Now you can compute anything. Now if I say, okay, give me 80% confidence interval, everything will remain the same in the formula except this number will change. So for 80%, can someone tell me what that number would be? Quickly. So what we're trying to say is that you've got something like this, and this is 80. So this is 10% here and 10% here. So in your standard normal, you just put 0.1, mu 0, sigma 1, and you get a new number. And that becomes the 80% confidence interval. Any dramas? All good? See this question here. See this interval again here. Did you get it, Marwa? Yes? This interval is just taking the sample proportion. Obviously, you've drawn out a sample, so you would know your sample proportion. And it also just talks about your sample size. That's it. So it just needs two inputs: the sample proportion and the count and the n. And then you can work it out, the interval. Any questions here? That's what confidence interval is all about. Now, all good? I'll just take this off the board. The next point to be noted here is, let's say you've drawn out a sample. Let's say you've drawn out a sample and your n was, let's say 200. And again, I'm taking the example of number of students using social media. So let's say you found that 140 are using social media. So what's your population proportion, Kisha? Population proportion is 140 over 200, which is 0.7, right? Yes or no? Not your heads. Say yes or no,
Yeah.
something, right? I need to hear that. Now, what actually it means is, if I'm going to go and calculate the confidence interval for this 95%, what I'm trying to say is 0.7 minus 1.96 over 0.7 times 0.3 over 200, comma 0.7 plus 1.96, 0.7 times 0.3 over 200, right? So what I'm actually doing is that I am actually taking off something and adding something to my sample proportion. When I'm taking off something from 0.7, it will go towards the left. It will decrease this value. It will give me a lower bound. This 0.7, if I add something, it is increasing 0.7. So I am getting, in this process, I am getting an interval, right? So the lower interval, I say Li, and the upper interval, or the upper bound. Now, what do you reckon? If my n here, the sample size, I'm point to ponder upon, if my sample size n is a very small number, let's say I've taken a sample n of not just 200, it's 20. What will happen to this boxed value if this is 20 now?
Becomes bigger.
It becomes bigger. Why? Because you've got a smaller number in the denominator. So this boxed value becomes
Larger.
bigger or smaller? Sorry, I got confused. When you've got a small number, 200 versus 20, So this becomes large, yes, because right, if it is 200, you've got a bigger number sitting. So this becomes smaller, right? So when you have a 20 here, this becomes bigger, right? So you have a bigger chunk getting subtracted from your population proportion. So your interval will become large. Same here. This is a big number in comparison to if I got a 200 in the denominator. So this becomes even more larger. So that means your range becomes quite high. But then if your sample, let's say this is a 2000, what will happen here, Ayushka? This number becomes really small, right? So that means you're not pushing too much on the left and you're not pushing too much on the right. So that means you've got a smaller number here. So now coming back to the example, if I had a sample of 20 versus a sample of 2000, I'm just making some figures hypothetically, and let's say you'll have a 0.2 to 0.9, and you'll have a point here. You will have a 0.5 to 0.7. What interval out of the two do you think is giving you better results, more precise results?
2000.
No. Yes, 2000, correct, this one. Because you've got a very shorter range, right? You've got more precise range to play with, right? Here you've got almost the universe, right? It's as good as saying from 0 to 100, right? Pretty much. Yeah. So, as your sample size increases, your confidence interval shrinks and you start to get better confidence. You start to get a better view of your population proportion. You're getting my point? So in connection, this value here, and let's say if I say, so this value here, which is 1.96 square root of p hat 1 minus p hat over n, this value actually decides how broad or how narrow your interval is. And I call this as margin of error. It's called the margin of error M. So this actually tells me how much precision I am putting in my interval. Does that make sense, guys? Yes?
Yeah.
Kisha, yes? Makes sense? More the sample, better the precision. All good? Now, this is 1.96, but that's 95. I just replace it by k. Your k could be a real number, greater than, less than, any real number, right? So this k is decided based on what is the percentage of confidence that you're after. So for 80%, I think, Chris, you calculated a number, right? For 95%, this k is 1.96, and so on and so forth. So this is the margin of error, and more your sample size, better your this interval is more narrow, right? You get better results. Yeah.
So is the k value like the z value?
No. The stuff that you found using z, right? So the k value is in your graph the lower bound and the upper bound. These values, let's say C1 and C2. These values, the boundaries which decide the percentage. So if I'm saying 95%, so this is 95%. So that value where your 95% starts, and that value where your 95% ends. Right? So if you find one, that will be a negative because you're going on the left of the mean, and the value which is on the right is a positive value because you're going on the right side of the mean. So these are the values on the x-axis. You getting my point? What is on the x-axis, Chris? What is on the x-axis? You made a point. You've got an f of x here, a probability density function. What do you have on x? What do you have on x? You've got the random variable x itself, right? Yeah, that's it. Any dramas in this one? This is a very straightforward stuff, not to be confused too much, right? That is what confidence intervals are all about, right? One more important point is you can find this using CAS as well. So in your CAS TI, if you go to menu on your scratchpad, if you go to menu, statistics, confidence interval, and there's an option called 1 prop Z interval. So you'll have something like, we've got three things there. So you've got the success, which is the X. Then you've got your N, the sample size, and you've got a C level. C level tells you what level of confidence you're after, 95, 80, 85, whatever, right? So if you enter that, you straight away get the confidence interval. You can try that if you want. We'll do a question and that'll make more sense, right? All good? Cool. So that finishes the confidence intervals at a concept level, right?